Good morning, everyone. My name is Guillermo Cuellar Maracara from the Universidad Autónoma de Nuevo León, and today we'll present our work entitled Evaluation of the Green Synthesis of Bismuth oxybromide via Plant Extract Mediated Coprecipitation. For introduction, pharmaceutical compounds are widely used in both human and veterinary medicine. However, many of these compounds can reach wastewater and surface waters, where their persistence may represent potential ecological and health risks. For this reason, there is growing interest in developing efficient and sustainable technologies for their removal. In this work, we focused on bismuth oxybromide or bismuth oxybromide in this form, a visible light responsive semiconductor that has shown potential for photocatalytic applications. Our purpose was to synthesize this material using a green and simple coprecipitation approach, incorporating natural plant extracts as reducing and stabilizing agents. Specifically, we selected orange peel and porcelain extract. The objective was to evaluate how these natural extracts influence the physicochemical and photoelectrochemical properties of bismuth oxybromide, as well as its photocatalytic performance toward two pharmaceutical compounds, acetaminophen or ACP or N-tetracycline or TCL. First, for these methods, we prepare the natural extracts. First, the natural extracts were prepared by washing the plant material, drying it at 50 degrees Celsius, and then heating 10 grams of the dry material in 100 milliliters of double distilled water at 70 degrees Celsius for 30 minutes. The extracts were subsequently filtered and stored. Bismuth oxybromide materials were then synthesized by coprecipitation. For the extract modified materials, bismuth nitrate pentahydrate was combined with acetic acid and the corresponding plant extract, while potassium bromide and sodium acetate were used in the second solution. The solution were mixed and with distilled water and ethanol, dry at 60 degrees Celsius for 12 hours, and finally calcined at 450 degrees Celsius for 4 hours. A pristine bismuth oxybromide sample synthesized with the extract was also prepared as a reference. The materials were characterized by X-ray diffraction, scanning electron microscopy, UFBs, diffuse reflectance spectroscopy, point of zero charge photocurrent response, and electrochemical impedance spectroscopy. Finally, the photocatalytic degradation experiments were performed using 0.5 grams per liter of catalyst and 10 milligrams per liter of either acetaminophen or tetracycline at pH 6. The experiments included 60 minutes in darkness to evaluate absorption, followed by irradiation using a simulated sunlight source at 30 watts per square meter. Well, for the results and discussion of this work, let me move to the main results. First, all synthesized materials retain the tetragonal structure characteristic of bismuth oxybromide. However, the samples prepared with plant extracts also showed some additional impurity phases. Interestingly, the use of this extract significantly affected the morphology. The pristine bismuth oxybromide exhibited a characteristic hierarchical flower-like morphology formed by interconnected nanosheets. In contrast, bismuth oxybromide synthesized with orange peel extract showed a more spherical morphology, while bismuth oxybromide synthesized with porcelain showed a more agglomerated structure. These differences suggest that compounds present in the natural extracts can act as structure directing agents during the synthesis. The changes were also reflected in the physical properties, like is shown in this table. The crystallite size decreased from approximately 40 nanometers for pristine bismuth oxybromide to 30.5 nanometers for bismuth oxybromide with orange and 28.2 nanometers for bismuth oxybromide porcelain. The band gap values remained relatively similar, ranging from 2.83 to 2.89 electron volts, indicating that the incorporation of the extracts did not produce a significant change in the optical band gap. The particle size obtained from same images also decreased from 4 micrometers for bismuth oxybromide to 1.84 micrometers for bismuth oxybromide with orange and 1.5 micrometers for the porcelain. We also evaluated the photoelectric chemical properties. Pristine bismuth oxybromide exhibited a clear photocurrent response, which indicates inefficient separation of photogenerated charge carriers. The electrochemical impedance results showed similar charge transfer resistance among the three materials, suggesting that the extract did not substantially modify this parameter. However, photoluminescence measurements revealed an important difference. Bismuth oxybromide orange exhibited the lowest photoluminescence intensity, suggesting a lower combination rate of photogenerated electron-hole pairs. This behavior was reflected in the photocatalytic experiments. For acetaminophen degradation, bismuth oxybromide and bismuth oxybromide with orange showed the highest photocatalytic performance, while the one with the porcelain exhibited a lower degradation rate. For tetracycline, the three bismuth oxybromide base materials showed a relatively similar degradation behavior under simulated solar irradiation. These results indicate that the effect of the plant extract is not as simply related to the optical band gap, but rather to changes in morphology and charge carrier behavior. Well, the conclusions to conclude this work, we demonstrated that bismuth oxybromide can be successfully synthesized through a simple coprecipitation method using natural plant extracts. The extracts influence the crystallocytes, particle morphology, and photoluminescence behavior of the resultant materials, while maintaining the characteristic tetragonal structure of bismuth oxybromide. Among the synthesized materials, bismuth oxybromide orange showed particularly promising properties, including lower photoluminescence intensity and enhanced photocatalytic performance toward acetaminophen. Overall, this approach provides a simple, low-cost, and more environmentally friendly strategy for preparing bismuth-oxybromide photocatalysis. The results also highlight the potential of natural extracts as useful tools for controlling the properties of semiconductor materials and for developing sustainable photocatalytic systems for pharmaceutical contaminated water. Thank you very much for your attention.